To introduce Matthew Roughan, someone I know quite well, who is going to speak to us today about a topic which is also a personal interest of mine, which is loss measurement and loss rates and modeling in the internet.
Thank you. So, I'm not going to tell you about the title of the talk yet. It's actually a really terrible title for this talk. It should be something like Statistical Analysis of Accuracy, not Statistically Accurate Network Measurements. But before I do that, let me just point out that I've been doing this work with Hung Nguyen, or at least the detailed work that I'm going to talk about today. So he gets all the credit for the good bits, and I'll take the blame for the bits that are boring or uninteresting for you. Won't be any surprise to anyone who knows me that I'm going to talk about network measurement. I have these two quotes I like that I always put up in front of students. I think that the underlying point here is that I don't have to persuade you that measurements are important. People have known for hundreds of years that measurements were really important. One of the nice things in the internet is that we're in this situation where we're actually really data rich. And after Walter's talk, you might have come away feeling a little bit like everything is bad, we have this horrible data, there's nothing we can do. My story is a little bit different. My story is the data is ugly, but there are things we can do. But we have to be a little bit careful how we do that. And people haven't always been that careful about what they do. So, let me have something to drink. My throat's going a little funny. Excuse me. It's on video now, isn't it? I suppose I should send a letter to, was it Coke? Yeah. So, we're in this funny situation in computer science where we're used to digital data, we're used to ones and zeros, we're used to things being right or wrong. And so when we make measurements, we often come away feeling measurement is the reality. And that's really the wrong thing to think. I always say measurements are always flawed. Maybe there's someone out there who's once upon a time found the perfect measurements, but certainly every set of measurements I've ever dealt with, and it's been a few these days, has had flaws in it, and they range over a wide set of problems. There are the obvious things like precision, and when I say precision, I should really be more precise. I should be saying things like accuracy and precision and resolution. And those are things that I guess I learned about in high school, but there are other things like ambiguity in the measurement, and Walter mentioned this when he talked about things like traceroute and aliasing. We have missing data. Missing data is a constant pain in this area. I'm sure it's a pain in other areas as well. Particularly, it's one of the things you find as soon as you start to collect big data sets, and when I say big, I don't just mean petabytes, I mean over long periods of time and over large scales, it's very hard to ensure that nothing goes missing anywhere. Then you have things like measurement artifacts, and that's something that you would love to get rid of. The reality is it's an ongoing process to make sure that those don't corrupt your data. And then there's this issue down here, which is the impact of the measurements themselves. And this is something that we often really don't pay much attention to in internet measurement or in a large number of fields. But the physicists know all about this, and they have things like the Heisenberg uncertainty principle. The underlying idea is that when you take measurements, they influence the system that you're actually looking at. So a classic example of this, I think Nick talked about net flow measurements. When you collect net flow measurements, the records are sent across the network. So net flow is measuring traffic, but it creates traffic as well. Now, if you're clever and careful, you do a bunch of sampling, much as Nick was talking about, so that the amount of traffic is negligible and it doesn't corrupt all of your other measurements. But you have to be careful, and not everyone takes that degree of care. So how do you fix this? Well, obviously I'm going to tell you a little bit of a story about this today. Common approaches are to sort of say, well, let's fix the measurement infrastructure, let's make better measurement devices, and that's a great thing to do. It's not really what I do though, so I'm not going to talk too much about that. Another approach is you just make more measurements and you use some statistics, and that's an approach that's been widely used over a very wide range of application areas, so we'll talk a little bit more about that. You know, statistics have been around for a while, so you might say, so what, isn't this all easy? Don't we know how to do statistics? Well, there's a couple of problems in the way. And the first one is just, I don't necessarily know what to do a priori. We need to think about this a little bit, and it's not just because I'm stupid. There are some actual problems here. And I guess, given the talks that we've had already, I probably don't have to justify these things too much. We've had several talks which have talked about heavy tails, non-Gaussian distributions at least. In this area, calling the Gaussian distribution the normal distribution is really foolish because it's not normal. It's almost the exception. Heavy tails seem to be far more common, although I wouldn't say they're completely ubiquitous. We see strong correlations, and we had, I think on yesterday, we had a talk about long-range dependence. Again, it's a phenomenon that's been seen in quite a few data sets. Frankly, at this stage, I don't really care that much about long-range dependence because most measurements are taken over a finite interval. And when you take measurements over a finite interval, you don't really care about asymptotic power law decay in the autocorrelation function. What you care about is the strong correlations you see over a short time interval. And we certainly see those in a large set of data sets. And I'm going to talk about that a lot more during this talk. And then we have things like structural biases in sampling. And I guess Walter again talked about this in the topology setting. So I don't really need to spend a lot of time motivating that. This one's perhaps a little bit of an enigmatic statement, but it's one of the things that I've worked on again, where you take a set of measurements and you take them because they're the measurements that are easy to take, not because they're the ones you wanted to take. Again, we had a couple of talks which talked about net flow. It's perhaps the ideal measurement for a lot of traffic engineering, a lot of these sort of analysis tasks that people have talked about. But net flow historically was quite hard to collect. And even today, there are legacy devices in the network which find net flow very difficult to collect. So one of the data sources that is easy to collect is a thing called SNMP, which is the Simple Network Management Protocol. But it doesn't give you what you want. It tells you link counts, it tells you total volumes of traffic, not where the traffic's going. It doesn't tell you what the applications are, the sort of stuff that Anya was looking at a moment ago. So there's often an inversion problem here to try and infer what you would like to know from a set of naively insufficient traffic. I'm going to talk about performance measurements in a second, but I just wanted to quickly go through a couple of higher level examples of these sorts of things. Particularly, we've had some good talks about network measurements, but they tended to be focused on a particular area of network measurement. When we talk about internet measurement, there's really three main things that we seem to look at. One is traffic, and we've had several talks about traffic. I've worked on estimating traffic matrices from linked data. This SNMP data we've talked about, interpolating the missing data that you have in this SNMP, which is one of the big pains with this data set. More recently, though, one of the things I've been starting to look at is the errors in these SNMP data sets. And you sort of say, well, shouldn't you have looked at that first? One of the things, this is a CCDF of the relative errors in a set of SNMP link count data. It's just counting the number of bits transmitted over a link in a 5-minute interval. And one of the reasons that I don't think anyone's ever done this picture before is, firstly, we knew what this picture looked like. We knew there were lots of small errors and a few really big ones. Engineers have known this for 20 years. I don't know why they haven't fixed SNMP to get rid of these big errors, because we have a fair idea what causes them, and I can tell you more detail about that if you care to get into the icky little details of SNMP. But the reality is it hasn't been fixed. We know that these things are out there, and consequently, engineers who are doing things like billing based on usage charges, they'd love to bill based on the peak usage, but they don't. They use the 95th percentile. They use the 95th percentile because that's somewhere around here, and you know that the errors up here are around 10 to the minus 2. They're really small. So that's pushing us back into that realm. So this picture was nothing that was unanticipated, but for me it's nice to actually see it, nice to actually measure it. Just another picture. This is one of the other dimensions of measurements, and Walter talked about this very clearly for a while, so I don't think I really have to spend too much time on it, but to just give you my own little picture of this, we've been doing some statistical assessments of how much data is missing from the AS topology data that Walter talked about. And it's a lot. So I don't know how clear this slide is, but this seems to wash out colors a little bit. We have a line along here, which is the measured number of links in the AS graph using Oregon route views, for those of you who know what that is. And you can see we're going in 04 from about 40,000 links up to, what's that, 65,000 links in January 08. So it's been steady growth, and we can see quite a lot of links. These little squares are our estimates of how many links there actually are out there, and you can see, broadly speaking, we're missing about 10 to 15,000 links. That's a really significant number to be missing, but the thing that I can't show you with this picture is that it's not a random sample that's missing. They're not missing at random. They're really, really not missing at random. They're a biased selection of links that are missing. And that really damages a lot of the studies that have been done using this topology data. Again, Walter talked a lot about this, so I don't think I'm going to go into any more detail than that unless someone wants to ask a question. The sort of measurements I want to focus on a little bit, though, are performance measurements, because I don't think anyone else spent a lot of time talking about these. So when we think about networks, there is the traffic that goes over the network, there's the network itself, but then there's also the resulting performance. And you can think of this in terms of systems as the traffic being an input, the network is a system, and the performance is an output. So if we had a good systems model, we wouldn't need to measure performance. And people have been trying to build these sorts of systems models for decades. They're queuing theorists, and I come from that background, so I have a lot of sympathy for that type of approach, but it hasn't really been successful. We don't have models that we really trust. We have a lot of different models, but none that I think anyone trusts enough to just not bother with these measurements. And so most ISPs now make some sort of performance measurement. And there are all sorts of different ways of doing this. But perhaps the most common, the classical way of doing this, is to use what's called active probing. This is very simple. All you do is you sit at your computer over here, and you type something like ping, and then an IP address, and you send a packet over here. And you measure how long that packet takes to get through the network, and whether or not it gets through the network, because the internet is a best effort network. So there's no guarantee that if you send a packet, it will get to the other end. Now, just sending one packet is pretty boring. Doesn't tell you that much. It tells you a few things, but not that much. So typically what people do is they send a series of packets. And they measure things like the average delay of those packets, or the jitter, which is essentially a measure of the variance, or they measure how many of those packets were lost. And the loss measurement is the thing that I'm going to talk about today. And the thing that I'm interested in is, given I take this set of measurements, what can I say? I know, if I send 100 packets and 10 are lost, I can say 10 packets were lost. But that isn't really very interesting, because what I want to say is something about the system. I don't want to say something about my measurements. I want to infer some quality of the underlying system. And in fact, I would like to say if 10 packets were lost out of 100, then the loss rate in my network is 10%. So the question is, can I actually say that? Or how many probes do I need to send before I can say that? How accurate are those probes? So we need to quantify what we mean by accuracy a little bit more here. And as I said at the start, I'm not going to talk about the measurement artifacts. You certainly, if you build crude methods of sending these packets, you can end up with horrible mistakes. And people like Daryl here have spent a lot of time trying to work on things like clock synchronization to make these measurements more accurate. What I mean here, though, by accuracy is just think about these as a series of samples from some underlying process or system. What can we say about that underlying system? We're going to take a series of samples over some period of time. Implicitly, when we do that, we're making assumptions of stationarity in the underlying process, and that's one of the things many people ignore when they're talking about these types of measurements, although much less so these days. We're also making assumptions about some sort of suitable mixing or ergodicity property between our samples and the underlying system. And that's a trickier thing to get right, but again, there are people like Darrell and Francois Bocelli who I think have really worked out most of the important issues in that particular problem. There's a very simple way of ensuring it, though, if you don't want to get too complicated, and that's you just send your probes as what we call a Poisson process, and those of you who know what that is will immediately recognize it. Those of you who don't, I wouldn't worry about it for the purpose of this talk. It's easy to send it packets as a Poisson process. If you do that, you have this property called Poisson arrivals, C time averages, or pasta, which guarantees this type of mixing property. So once you have these, once these assumptions are hopefully true, and they do limit what you can do in this sort of measurement domain, then you can do things like estimate the variance of your loss estimator. And that's what I mean by accuracy. I'm going to assume my loss estimator is unbiased, so the variance really tells me all I need to know about that estimator. So we're really talking about the accuracy of this estimate, not the accuracy of those underlying individual measurements. So what's hard about that? Any guesses? Okay, so I know a few people in here have done performance measurements like this. So you'd expect at least a couple of guesses. The hard thing here is that these measurements are not independent samples. So I have a trite little quote and a little example to go with it. So this is my little quote. There's a more subtle point, and this is a sort of amusing aside, but there is a more subtle point here, and I'll get to it in a second. But I have a picture to show you, or a couple of pictures. It's a unicorn. I guess most people would recognize it. If you do a search for unicorn on Google, I did this just the other day because I was doing this talk, and you come up, if you do the image search, you get something like 3 million images, and I didn't check each one individually, but most of them look something like this. It's a horse with a horn in the middle of its head. So there isn't an animal like that, at least not that I know about. You could glue a horn, I guess, on a horse, but there isn't a natural animal like this. So you go back through history and you try and work out where this animal came from. And there's a Greek guy called Statistics, who was a member of, he went to the Persian court and he wrote this thing called, let me make sure I get the pronunciation right, Indica. And then various people like Aristotle and Pliny basically copied him. They took essentially the same little, very short, very vague description, copied it, added a little bit, and this happened for another couple of thousand years. A couple of thousand years worth of Chinese whispers produced this thing. Plus, a little bit of other stuff going on here. I mean, there is an animal with one horn in the middle of its head. It doesn't look too much like this, the unicorn. And then there are narwhals, and these guys have this nice long straight horn, which of course people would cut off and proudly produce and say it's a unicorn's horn. So you put a couple of these things together, and this myth somehow developed into a large thing. It's kind of a trite example, but the point I'm trying to make is if your data, these 3 million images, is all based originally on one measurement or one statement, then the fact that there's 3 million of them doesn't really help you. And that's really true in measurements. When you have measurements that are highly correlated, and usually this is because they're on some process which isn't entirely decoupled in time in this case, then the extra measurements don't give you as much information as you might think they should, certainly as they would if they were independent. So the obvious question then is, are packet probes correlated? I don't think the answer will surprise too many people. Yes, they are correlated. They're quite strongly correlated, and they get more correlated the closer together they are in time. And this shouldn't surprise too many people, because at least a couple of people in the audience have worked on tomographic problems where they explicitly use this type of correlation to try and get multiple probes that have similar behavior, even though they're going along different paths, or slightly different paths. The short-range correlations can be quite strong, even if there are no long-range correlations, and this goes back to my point at the start. I don't care about long-range dependence in this application because my measurements are always over a finite time, usually a fairly short time. We're talking about times of the order of, say, 5 minutes to an hour. Fairly short time periods. The other thing that's kind of interesting, and I guess I'm not going to dwell on this too much today, is these correlations tend to be load dependent. As the load on the system increases, you tend to see higher degrees of correlation. And I may get a chance to talk about that if I don't run too far over time. So does that actually matter? And the answer for me is very much yes. Why is that? Well, I like building the research I'm working on around the applications for this work. And the common applications for these sorts of measurements are either in maintaining network quality, where what you want to do is produce a signal when there's something going wrong, or in network business relationships where two organizations, one of them might provide transit for the other one that's carry their traffic, but the contract involves signing a service level agreement which guarantees, say, no more than 10% of your packets will be dropped. So in either of those cases, the interesting question is, how do I know? How do I know that more than 10% of my packets have been dropped? How do I know that something's going wrong in my network? I need to have some idea of how accurate my measurements are, and we've just seen that that's not necessarily going to be too easy with these sort of performance measurements. So let's go into a little bit more detail. It's not hard. I realize this is the afternoon of the last day of a very busy week for most of you, so I'm not going to throw anything too hard at you. But I do want to get a little bit of the detail of what's going on here. I have an indicator function I. I didn't say that out loud when I was preparing the talk. It sounds a bit silly. I should have done ij. And II is 1 if the ith packet is lost, and it's 0. Sorry, which way around are they? Yeah, it's 1 if the ith packet is lost, and 0 if it's safe, if it gets there successfully. So the standard estimator for the loss probability is just the estimator we would use for any sort of binomial process, Bernoulli process. It's 1 over n times the sum of these indicators. And I'm not going to change that. That's a nice unbiased estimator for this loss probability. But the thing I do want to look at is the variance of this estimator. And it's almost stats 101 to calculate the variance. It's just 1 over n squared times the sum over I and j of this guy, which is the autocovariance function of the loss process. And these are the times between the I and jth measurements. And again, we're assuming this is a stationary process, so this thing doesn't change over time. So what's the big deal? Well, the big deal is, firstly, most people ignore this entirely. Most people either, when they're doing these loss measurements, don't report any information about the variance of those loss measurements. Or if they do, they base it on the assumption that they're independent, in which case this thing just looks like a delta function. So you miss a lot there. this variance actually should be quite a lot bigger than it would be if you use that independence assumption where most of those guys are 0. What else could you do? Well, we could try estimating this. It's a nice little estimation problem. It's not a particularly sensible estimation problem to try and estimate that thing directly. Let me try and explain why. We have r, tor, I, so these things, potentially there's n squared of them, but we have n measurements. It's never a good idea to try and estimate n squared things from n data points. So we could try and do something like fit a parametric curve in here and smooth out the estimate that way. But I'm going to suggest a different technique, which is based on a model for how we think losses might happen. Oh, so this is my slide, just telling you what I told you. I'm not going to spend any time on that after explaining it all. So model plus parametric estimation. We could come up with a lot of different models here. And you know, there is always this tension in modeling between simplicity, parsimony, and on the other hand, having something which is really accurate and really reflects what's going on. And there's never a right answer. So we have to compromise in one direction or the other. And our model that we've chosen here is definitely a compromise, but we've gone a little bit towards accuracy compared with some of the previous work. Typical previous work has used Markov models. There are various ways you can apply a Markov model here. The most simplistic way of just assuming that measurements follow a simple sort of on-off process, which is Markov, doesn't work too well at all. So what people tend to do then is include some of the history in the Markov model. That's kind of awkward here because it's easy to include the history of on-off when they're just on-off states. But we're trying to model an underlying process here. We're trying to model the underlying continuous time process. And to keep that history around, we need a lot of states in this Markov process to even approximate it. So Markov models don't work too well. But we don't want to get too much more complicated than that. And so the approach that we've taken is to use what's called an alternating renewal process. An alternating renewal process is a very easy idea to understand. It's a process that goes from off to on and then off again. It alternates between off and on. And whenever it switches, you have what's called a renewal point. And at a renewal point, you forget the past. You forget anything that happened beforehand. And that's a big assumption. That's not quite true with our data, I will happily admit. But it's a much better approximation than the Markov approximation, where you forget the history at every time point. Why use an on-off model? Well, it fits some of our intuition about how losses occur. There are two main processes that lead to packet loss. One is congestion. That's a queuing process. A buffer fills up, and then for some time packets get dropped because the buffer is full. The buffer empties, and then for some time period after that, packets can be accepted. So you get this on-off process of losses. And some queuing processes, at least, these switching points between those two states are renewals, although I'll happily admit that for realistic queuing models of the internet, they're most likely not renewal points. The other type of event that causes loss are routing events. Typically, these are what we call routing reconvergences. When something changes in the network, routes change, and during that period of change, packets can be dropped because there's either no route to their destination or there's a loop which they get stuck in. So in either of these cases, an on-off process makes sense, although the renewal structure does impose a little bit here. But again, we need that to try and maintain some degree of simplicity here. So this is our alternating renewal process. It's on and off times are independent. The on times are IID, that's identically identically distributed random variables. And we go on one step further, which is to parameterize these on and off times as gamma distributed random variables. Why gamma distributions? Well, if we chose an exponential distribution, we'd be back in the world of Markov processes, and we know that that doesn't work too well. We tried it, it doesn't work too well. So what's the first thing you try after an exponential? Well, a gamma distribution includes the exponential as a special case, but it allows a much wider range of behavior, all the way from an almost deterministic behavior back to a highly skewed, almost heavy-tailed behavior. So it encompasses a wide range of possibilities with only 2 parameters, so it's still relatively parsimonious. So we have one gamma distribution for the on times, and we have a different gamma distribution for the off times. One of the nice things about this simple on-off renewal process is if we know these parameters, if we can work out all of these parameters, we have a closed form for the Laplace transform of the autocovariance function. So once we know this, calculating the autocovariance function is simply a numerical process of inverting a Laplace transform. And again, there are good numerical techniques for doing that and have been for some number of decades. So the question is, how do you estimate the parameters of this process? I don't have time to go into every single little detail here, but we rely on a little bit of magic from an area called hidden semi-Markov models. Now, probably a bunch of you have heard of hidden Markov models. A semi-Markov model is just a Markov model where the states have a time associated with them, and it's not an exponential time. It could be some general distribution. In this case, it's a gamma distribution. So a hidden semi-Markov model is essentially the same sort of idea as a hidden Markov model, but where we have this time to estimate as well as the state transition probabilities. The techniques that people use to estimate these things are very closely related. We use an algorithm called the forward-backward algorithm. It needs a little bit of customization from the standard literature in order to get it to work on this particular problem and get it to work efficiently. But it's not an intrinsically hard thing to do, I think. The thing that we do have to make sure that we get right, though, is, let me explain this picture really quickly. The top solid line is going to be my on-off process, and the arrows show my samples. Now, if I just took those samples and tried to infer when the on-off times were directly, I'd end up with a process that looks like this, because I don't see, for instance, that A1 interval. I don't know it's there. So the process we're using to estimate the behavior of this system has to be able to guess at these little hidden on-off transitions. Otherwise, we tend to overestimate the length of these intervals fairly dramatically. And that would overestimate the autocorrelation function. If we tend to make these intervals really long, we tend to extend the correlations and make perhaps too big an inference about the variance of our estimate.
So during a congested period, I guess you have a non-zero probability of loss, but it's still not 1.
In what we're doing, when we're in an on state, we set the probability of loss to 1. But you could certainly come up with a model where you made that also a parameter of the system. This seems to see how well this works, though, before you get upset.
What are you doing the estimation based on?
What are we observing? So we're observing these samples of whether or not we lose a packet or get a packet.
Do you control the time? Or you know
We control the timing, yeah. But at the end of the day, that doesn't actually matter too much for this algorithm. So in all of the measurements we've done, the timing of these things, they're sent as a Poisson process. But the algorithm for doing estimation doesn't rely on that. It does make it easy to justify this assumption of mixing and ergodicity at the start. So I don't have that much more time, so I'm not going to talk about simulations. Simulations, I'm sure, would bore all of you. I'm going to talk about some real data for this. We've done a bunch of experiments. We've done a large number of experiments now to try and assess this. We have at least 4 different types of measurements. Some of them are from Planet Lab to Planet Lab nodes. Planet Lab is a dedicated system designed to allow people to do things like these measurements, and it's distributed around the world. It's fantastic from that point of view, but it's sometimes felt not to be that realistic because it's in academic networks typically. So we have a series of measurements that we set up ourselves. I guess partly also because we wanted to test the way the measurement infrastructure interacted with this between EPFL and Australia. Between EPFL and Australia is a good path to look at because Australia is so far away, there's bound to be some place with loss, somewhere in between. We looked at web server probes, and I guess one of the things I want to emphasize here is, although I've talked about this as measuring properties of a path through a network, the same idea is equally applicable to measuring how many packets are lost at the server. And we've looked at web server probes and DNS server probes with a view to trying to understand server behavior. So one of our standard traces for this, and this doesn't apply to the DNS server data which we got from the guys who wrote about Queen, those of you who've heard of it, involved 10,000 40-byte UDP packets. They're sent as a Poisson process, as I mentioned, roughly 10 packets per second, or an average 10 packets per second. And then once we got these traces, we filtered out the ones that were obviously not going to be helpful to us. And there were two criterion for this. One of the criterion was they didn't have enough packet loss to be interesting. So if you lose one packet out of 10,000, there's not a lot you can say about the autocorrelation of the process. And the loss is so low that it's not that interesting anyway. The other thing we filtered out was obvious non-stationarity. We use a fairly crude block-based test, so we look for blocks where there's a large change. This is because there is this underlying assumption of stationarity in a lot of this measurement work, but we didn't want to be too strict about this. So it's a fairly coarse test, and it's only excluding things which by eye you would say were obviously non-stationary. We want to have a test which is reasonably robust to all of the uglinesses you get in real data sets. Once we've done all of this, we had around 1,100 traces. And we've tried it out on a bunch of these sorts of traces. Very quickly, these are some of the results for parameter estimates. This is the scale parameter for the on and off periods. And these are the shape parameters. I guess the only thing that really matters here is if the shape parameter was 1, we'd be back in exponential land. We'd be back where Markov assumptions work reasonably well. And we can see that certainly for the on times up here, the sort of median value is around 5. So we're very far away from that realm where the exponential distribution works. When we look at these are the times when packets are being lost. They do seem to be distributed around 1. Might be more reasonable to try and model that part of it with an exponential, but certainly these off times, the times when packets are successful, don't seem to look anything like an exponential distribution. The other thing I have to tell you about a little is how we're testing this. There is no good way for us at least to test this, because we don't know the real loss. If we knew the real loss, or if it was easy to get that, we wouldn't have to take these sort of measurements in the first place. So there are very few people out there who can know this real loss. You can imagine an ISP instrumenting its network in a great deal of detail to measure it, but even then, it's a measurement over some sort of time interval. A lot of the time you use these sort of measurements for prediction, and so as a predictor, you still would like to have some statistical idea of variability. So what can you do? Well, there's a test that can tell us when we're wrong. We can't have a test which tells us when we're right if we don't know the ground truth, but certainly we have a test which can tell us when we're wrong. And that test is simply to look for consistency. So what we do is we take our measurement sequence, 10,000 packets, and we break it into 2 sequences. We select randomly from those 2 sequences and separate it into 2 subsamples. Now, one of the nice things about a Poisson process is when you do that, the 2 subsequences are both Poisson processes at half the rate. So if we measure the loss from one and the loss from the other, they should be consistent. And the way we can test whether they're consistent, there are a couple of ways we could do this statistically, but a nice visual way is to look at confidence intervals. So that's what I'm going to show you. Well, I'm going to show you something else first, actually. I just wanted to do one other thing before we get to the confidence intervals. Think about consistency. If we look at the loss estimate, we can put a variance on that, and those variances should be roughly the same for the two different subsamples. And indeed, when we use the hidden semi-Markov model technique, we see that these are clustered along a diagonal line, which indicates that they're roughly consistent with each other. When we use the empirical variance, and this is this technique I mentioned at the start of trying to directly estimate the autocovariance, you get garbage. These are empirical variance estimates. They make no sense. They have no relationship to each other. They're completely inconsistent. So we can throw that technique out the window right at the start. I don't want to say too much more about that. This is the confidence interval graph I wanted to show you. The red curve shows one estimate from one set of data, and the blue curve we've done with confidence intervals just to show consistency comes from the other set of data. And the thing that's worth observing is that in the majority of cases, in fact, this is a sample of about 70 traces. We have actually done this with 1,100 of these traces. In 92% of cases, these 95th percentile confidence intervals overlap in the way that you would hope. Just to give you a point of comparison, if we assume that the measurements were independent, we got rid of all of this modeling stuff and just used the independence assumption, you'd get these confidence intervals overlapping 63% of the time. Now we'd like this, instead of 92, we'd like for 95th percentiles these to be 95%. So this is not perfect, but it's a hell of a lot better than 63%. The other thing that I really want to point you to here is the fact that these confidence intervals are big. We're talking about, for one of these subsamples, 5,000 measurements, and yet when we're measuring these loss, which most of these cases that we have here are of the order of 1 or 2%, the size of those confidence intervals is often going from 0 to 2 or 3, or in one case up to 4.5%. Now, it's tempting to say, well, okay, make more measurements so that you can make that better. But as you make more measurements, you could stretch them out in time. That would work, as long as stationarity didn't get broken. But if you keep the same interval of time as you make more measurements, the measurements get closer and closer together, and so the correlations between them actually increase. And so these confidence intervals, they go down, but only marginally. Not as much as they should. Certainly not by the 1 on n sort of factor that you would normally expect as you increase the number of measurements. So I can see Daryl's standing there waiting for me to finish. So let me get through the last couple. This is another data set. This is the web data set. And you see the same sort of thing, but in this case, these black guys are, again, the intervals that you would have obtained if you just assumed these things were independent. And they don't overlap the red curve in the way that they should. A lot fewer of them, in fact, overlap than should. And this is the DNS data again. And I guess one of the things I'm trying to show here, apart from the fact that independence is a really bad assumption to make here, is that this technique is reasonably robust to a whole lot of different underlying issues. We're using completely different types of data here in each of these cases. So the conclusion, well, obviously the high-level conclusion is you should be careful what you do with measurements, but there are some useful things. It's not all a doom and gloom story. We can make progress. But we do need to deal with the difficulties in these data, and correlations is a common thing that we have to cope with. You might say, what if I measure every packet? There are techniques out there which potentially could do that. Even if you measure every packet, you still want to operate in a mode where you're trying to make predictions in a lot of cases. You don't necessarily want to say what's happening today, you want to say what's happening tomorrow. So again, you need variances of estimates and predictions. And so the same type of theory applies, even though it might not apply to the actual loss measurement itself. We have a much longer technical report about this. We have a set of MATLAB code that will let you do this estimate without all the pain of trying to understand the modeling and all of that kind of stuff. So please, if you're interested, we're looking for people who have data sets that we can add to our list of tests of this and make sure that it works as well as we believe it does at the moment. By the way, one of the things I'm not insisting here is that this model is perfect. I certainly think there are people out there here today who could probably improve on it as well. But it's certainly a hell of a lot better than the existing state of the art. And I guess one of the things that I've just finished with is saying there are hundreds of papers now written which use loss measurements or talk about loss measurements. As far as I know, none of them actually take into account these correlations in this sort of way. And so there's a lot of misleading work out there. There's a lot of measurements which, without this sort of assessment of the accuracy, it's very difficult to say whether or not the conclusions of the paper are correct or not. So perhaps I'll leave it on that, and maybe someone out there will ask me a tricky question about that particular statement. Hey.
Hi, yeah, that's very interesting. And one point, though, that I don't quite get, and I'm probably just missing it, is at the end to validate, you sort of work with these, you thin your Poisson process, split in the two, and then use that to sort of assess whether you were doing something sensible. But if you can do that, why not just thin it a few times and do some sort of cross-validation or bootstrap to get a confidence interval?
Yeah, so the bootstrap is kind of an interesting idea, and I'd like to have a play with that as an alternate means of doing this, but I don't actually know how to do that with this sort of correlated data. So maybe we could talk about it afterwards and
Not sure either. But
come
I
out.
think like if that validation is meaningful, there ought to be a way to use some multiple thinnings and get.
Yeah, I understand totally what you mean. I think one of the nice things about the Poisson process is you can do that. Not everyone wants to sample using a Poisson process, and it gets a little harder if you have something that's not Poisson, perhaps. But other than that, I think it's a good idea. I'd like to work out how to do it. Francois?
Question, but so in some cases you can reduce the variance by reducing the variance of the exponential intervals by moving to gamma probes or things like that.
Yeah.
I mean, in this case, if you try this, would it reduce the variance of the estimators?
I think it would, but not by a major amount. I think, you know, the work that you've done on the variance dependency on the sampling stream, I think that all applies here. But I don't think it gets rid of the problem. The underlying problem is the correlation between the measurements, and that doesn't go away, so you still have an issue that you have to deal with. And one of the nice things about the way Hung set up this code is there is no assumption that the sampling sequence is Poisson, so we can do it with a gamma distributed series of probes, the sort that you sort of propose. We can do it with a regular sequence of probes even, although I'm a little skeptical about whether people should be doing that or not, but yeah.
But so if the autocorrelation function of this on-off process, non-Markov, alternative Newman process would have convexity properties, then you would have a reduction of the variance of the estimator by moving from.
And under these assumptions of the on-off, we definitely have that convexity property in the. I'm sure we have that convexity property in the autocovariance function.
For all types of gamma distributions. That's the.
I'm pretty sure, but we could test it out if you like. I think it's pretty. It should be pretty easy to show because we know the Laplace transform. Yep.
To follow up on your discussion with Rob, I'm not an expert at all on Bootstrap with time series, but it is a fairly well developed area, and my rough understanding is that the trick is to take blocks of data rather than just randomly sample, so you maintain correlation structure. But if you can take the blocks far enough apart, then they're sort of independent.
Yeah.
So my sense is that the delicacy there is in the width of that window and how far apart, and that's the trade-off you're doing with compared to what you're doing, which is building models structure on. So my guess is that it wouldn't be too hard once you tap that literature, and I can tell you the few roughs I know.
So one of the problems we have is that you have to go a long way out before you lose this correlation structure, and it does get stronger as you get close together. But the top picture here shows you an indication of it's kind of the time scale at which the correlations drop below a certain factor. I can't remember the exact threshold. For the 1100 runs, it's an attempt to measure this autocorrelation function or try and get a scale of how big the correlation is. And you can see that in a large number of cases, it's more than 100 packets. It's sort of 10% of the data. So perhaps you could do 10% blocks. I don't know, is that enough to get Bootstrap up and
What I
running?
was going to finish up by saying was that, so the interesting question is really whether you can nail that well enough with your data compared to the structure you put on with your model,
Yeah.
but perhaps nail just what you need to by assuming the model structure.
So when you say blocks, what do you mean exactly? Do you mean you restrict measurements to blocks that you separate?
Time blocks.
Adjacent?
Yeah, and then usually separated would be one way,
Right.
or maybe overlapping not too much, or that there's a whole, apparently there's a whole art and science to it, but I don't know it beyond that.
But that would be if you're fixing your budget for a number of observations and you can pre-vary everything else, whereas the whole point here is like you wanted to answer in a fixed period of time and you can't exceed the stationarity issue as well. So you
These usually assume stationary. Yeah, I mean the idea of the fixed time is what's going to, in general, get these things. If you have a long enough amount of time and you're able to nail the window widths and get that right, then you can do a reasonable job apparently. There's some other flavors that I don't know what those flavors are.
Yeah, I'm sure there's some other approaches like this that you could use to tackle the problem. The nice thing here is we do have some intuition about the underlying process, which is, we can exploit that and perhaps do a little better than the blind statistical approaches, but it'll be really interesting to do a comparison. Are there any other questions?
Just follow up on that, there was a survey article by Chris Pawlikowski about estimation of statistics in simulations, which addresses similar issues. And I think you could, as well as the blocks method, is that a method based on...
Actually, if you go back through the simulation literature, this issue has appeared going back even to the 50s. And there's a paper by Morse which looks at this type of issue for delay estimates for simple queuing processes like the MM1 queue, and then you look at some of the work by Ward-Witt and so on, and again they use these same sorts of arguments to look at how long you need to run a simulation for in order to get a certain sort of accuracy of results. So a lot of the inspiration actually comes from that literature. I don't know the paper you're talking about specifically.
I was wondering what was the intuition with picking the gamma distribution for the on and off times, because it seems for me that's somehow crucial for your method, whether they will fit the actual
Okay, so the motivation goes like this. Exponential doesn't work. The next thing you try is gamma. It wasn't going to be the last thing we tried, but it worked. So you could certainly think about doing something else. And the one nice thing about the gamma is it includes the exponential, but it also has this wide range from being almost deterministic to a highly skewed distribution. So you can allow a bit of flexibility, and by doing that we got to see a little bit about our data in terms of this sort of plot where you can start to see what those intervals actually seem to be like. And in this case, the on intervals where k is 5, that's starting towards the deterministic end of the spectrum, but we're not seeing the same thing for these sort of loss periods when we're losing packets.
One more question.
It's just a quick question. What's going on about k? K0 equals 20. What's it there?
Actually, that's probably MATLAB. What MATLAB does is if you set a histogram with an edge, it dumps everything into the bin at the end. So actually, there's a bit of a tail on there. And we probably should have been a little bit more careful about extending that out further so that you can see how far it actually goes. But I don't think that's a real block at 20.
Yeah, that's what it was. Okay, but I've got a pile of questions, but I think I'll take those offline. So let's thank Matt again for an interesting talk as always.